So it's a pleasure to be here for the last session of the summer school, the first inaugural TAILOR summer school. And I'll be presenting to us about agent-based modeling for social simulation. And I have to give a thanks to my colleague Igor Nikolic for helping with the slides here. Okay, let me see. Okay, there we go. Hopefully the second slide you can now see. Good. Okay, so agent-based modeling. So I mean, what is this? Well, it might look something like this. And so here we have, this is an architectural situation. And here are these little blobs here of people. And the question is, there's an emergency from this building. How do we evacuate? Or better asked, how would people evacuate? Because you can't really say to everybody, well, please, you go there, you go there. I mean, people, evacuate, okay. So, I mean, how do we know whether we have enough exits or whether the exits are in the right place? So we use AI here, so agent-based modeling, to give us some insights into how to evacuate this building and to answer some of these questions. Okay, so that's my way of introduction. So this is what we'll be talking about for the next, 90 to 100 minutes or so. So first of all, I'll give some motivation, and that's in the context of social technical systems. It's the kind of thing we're going to study and analyze using agent-based modeling. I'll then talk about the philosophy, if you will, and that's generative modeling. I'd then like to do a little bit of hands-on with a system called NetLogo. So we'll come to that later. So there'll be some hands-on things for you to try. And then we can give us your conclusions and about resources at the end. Okay, so let's get started. Let's dive straight in. So let's talk about social technical systems. Okay, so let me see here. I wish I could actually do slideshow. A great risk. I'm going to try doing it again because it get better animations if this works. Okay, we're risking it here. Okay, let's do it like me. If it all suddenly breaks, we'll revert. So what's a social technical system? Why are we talking about this when we're talking about AI and a trustworthy AI? Well, so here I'd love to see all your faces if we're doing this in person and to ask you, well, who knows about, what is a social technical system and so on. So maybe you can have a go in the chat. If you're familiar with social technical systems, you've heard the term, that kind of thing, could you say so in the chat? I'd love to get a few messages and see from you. Okay, no responses in the chat. Okay, fair enough. Well, let's carry on. So social technical systems have the social side, of course. So that means people and processes and so forth. And also the technological side. So here we're talking about things like data and systems. And of course, the intersection of these two is going to be complex. This is the point, right? So in a social technical system, we have this complexity emerging because we have both the people and the systems. So when we talk about trustworthy AI here, we can't simply say, okay, let's make some nice AI algorithms and do the technology side, because there's also the social side. And this is recognized indeed in a number of the TAILOR work packages, for example, work package 6. So this So let's talk about complexity. So before we come to agent-based modeling, let's talk about why we need to do it and what it is we're going to model. So complex systems. So here we go. The question is, what is this? And is it a complex system? Well, this is a car tire, right? Is it a complex system? Certainly the person who first invented a wheel was a genius, but we wouldn't argue it's a complex system in itself. So what about this? Is this a complex system? This is a car, right? Which has several wheels and a bunch of other stuff. Is this a complex system? Well, we might rather say it's complicated. It's not simple like a simple single wheel, but doesn't have complexity in itself. By contrast, this is a complex system. So here we have the problem of, here are all the bits, now assemble the car. Right, so driving a car is a little bit complicated, you have to learn, but assembling it, okay, now we have great complexity because, of course, you could assemble things in different ways, and you could make not just the car that was originally designed. You could do some modifications to it. So complex systems have this kind of inherent, multi-possible directionness to them. There's many ways in which they can adapt, they can evolve, they can be used. Okay, so here's another good example of a complex system. It's like a disassembled car the complexity comes out of a sum of parts. Fish, if you can't quite make it out, and no one like planned, there's no human plan for the fish to make this kind of shape here. They kind of do it, well, you might say it emerges. The shape which the fish follow kind of emerges from just the simple, if you will, behaviors of the individual fish and how they interact with each other. And this really is where complexity comes from. It's this non-linear global behavior coming from the interactions of, let's say, relatively simple interactions of individuals. Okay, so the complexity emerges from how we start out with simple things interacting with each other. And we get effects that are not expected. I mean, who thought fish would make this kind of spiral shape? Okay, so far so good. Okay, complex systems, and these are some of the properties of complex systems. I've mentioned some of these words already just now, like non-linearity and emergence. Other words people sometimes use is things like randomness, path dependency, robustness or non-robust, instability. If you saw the original Jurassic Park film, that film talked about the notion of chaos and chaos theory, where there's unpredictable paths. This is just the emergent non-linearity in a complex system. Okay, but leaving aside Jurassic Park, we've already seen examples of complex systems around us. Okay, so complex systems. Now, here's the challenging thing if you're a computer scientist. Social scientists study complex systems and they ask different research questions to which are typical in computer science. So in computer science, you're writing a paper for ICHGAI or whatever, you'll ask things like, is this a new algorithm? Does it work better? Show me the area under the curve, etc. Where does the data come from? And what about generalization? Well, so these are the kind of questions we have on the screen here. They are, well, I'm looking at those fish making that circle. Why is this happening? Or they're looking at a car and it's reassembly, and they ask, well, how does it affect these stakeholders? They might ask, okay, these actors are interacting in a certain way. What are the values behind them? What values are exposed by the action? All these different factors, how are they linked? Or they might ask, for example, what policy should the government take? Now, AI can help with some of these questions, but it can't directly answer the questions themselves. I mean, what policy should one take? Is an algorithm going to tell us? Okay, no, we start getting into a broader discussion. Okay, so what's the point? We have complex systems, and social scientists ask these kind of questions about the system. Okay. Okay, so far so good. Okay. Is appropriate. So computer scientists might be interested in a needle in the haystack, but social scientists want to know about characterizing the haystack itself. It's a different mindset, a different way of thinking. And this is important when we come to the study of complex systems and in agent-based modeling, as we're going to discuss today. Okay, so let me put up a slide about what is an agent. So I put this up because different communities have different definitions. And the definition, say, often used in AI is not necessarily the definition used by other communities. Okay, so if we just look at, let's say, computer science, there's maybe 3 schools of agent thinking. So the first is kind of a traditional, I call it the AI view. So agents are autonomous identities solving problems. So here's a reinforcement learning agent, and it's going to solve this, I don't know, game for me. A second view is of multi-agent systems. So here we have a whole set of agents, and the question is how I put in control, how to control their behavior. And the third, and usually, and that's all. No, it's much more about simulating phenomena we see, often from the real world. So those fish in the circle. Focus, the thing to understand is, the focus is not, we're going to build an agent to solve a problem, nor trying to control a distributed set of agents. We're simulating something, and a system, and trying to understand something about it, trying to answer some of the questions which a social scientist might ask. Okay, so I start with this because it's important to understand this kind of distinction in ways of thinking. So far, so good. I'm looking at the chat in case someone would like to have a question. I'm looking at the chat in case someone has a question. No questions so far. What's the big? Well, we start from these agent factors in them, and what model social reality with the agents and the interactions. So again, we're studying some, let's say, real system. We want to get some model of it, right? And the social aspect is important. Okay, so it's bottom up. We're not going top down. We're going bottom up. The key question, you may have guessed already, is how could the decentralized and local interactions of a bunch of heterogeneous autonomous agents, how could it generate the observed regularity we see in the system? That was a really long sentence. I mean, look at the fish, right? As I mentioned earlier, the fish, they do their own little thing and they interact with their fish neighbors, and they have these, they're autonomous, if you will. But look at this observed regularity, this pattern, this circle, this curve, which is generated. How could the decentralized individual interactions end up with this system level emergent effect that we see? That's the key question. Well, what does that mean? Well, before we get into it, let me give a brief history. So agent-based modeling has been around for some time. It became a bit popular in the 1990s, thanks to some work that people who did cellular automata. And further back, if you know what I think it is on the left, you'll smile about it. And it was, there you go, animation. That's a game of life for you. Okay, what are some of the applications? Well, here are some. Energy market deregulation, for example, in the 20s. Another epidemic, classic example of agent-based modeling, and very contemporary. So we saw a lot of new agent-based models coming out last year, and I've got a slide on that. Employment at the national scale. Tell me about how the economy works. This particular example, I think, had 100 million agents in it. Model of the US. University admissions. Who gets admitted or not admitted and why? And even collusion among the nations voting in the Eurovision Song Contest. Agent-based model of it. And for example, there we go, there's a winner. Not saying anything about collusion there. Okay, I mentioned agent-based modeling had a lot of examples came up in the last year or 2 years because of COVID. So here's one. This is on GitHub. You can go have a look. Let's make a click on. There we go. This is the COVID sim. This was a model first developed in early 2020, so last year after things started, by the MRCC Centre at Imperial College London. This was a very influential model. They wrote a paper in a Nature journal about it, and it's argued it changed the course of the approach to managing COVID within the UK and maybe in Europe or even worldwide. Changed the course of government policy internationally based on an agent-based model. Okay. So now you start asking questions like, well, what did the model do, and did it do the right thing, and why do they base policy decisions on it, and what were the assumptions in the model, and so on and so forth. And we'll come to some of these questions later. So agent-based modeling has a whole bunch of real-world uses in the last 20 or so years. I'll very briefly give you a case study, just to wrap up our introduction here. This is an industrial network in the northeast of the Netherlands. And so the modeling here is looking at different companies. So here we go, I had a company agent who looks a bit like this. The details really don't matter here. The key thing to know is there's some inputs to the agent, there's some outputs, and there's some things that happen in the middle. So there's technology and economics. And there's some rules of inference happening. And we have a whole bunch of these a company and other agents. They have different goals, if you will. They interact with each other. And the interaction between these heterogeneous agents actually generated a structure. So here we can see the consumer is at the center. He's some type of a power plant. So the question being studied was the transition, the energy transition to biofuels. Yeah. And this structure can be matched with a real world reality. Does it match? What do we learn from that? If it does, then what questions could we ask of a model that would help us answer questions in the real world? Okay. So that was just a brief case study of the kind of thing that gets used. Okay, so we've covered a lot already, and it's very important to give our foundations. So the research questions in social science concern causality and explanation. We're not looking here for a fast algorithm or a better training for our neural network, whatever. We're asking questions about causality and explanation of usually some real world system. Why agent-based modeling? Because it brings in a bottom-up perspective, which lets us look at the emergent effects based on simple interactions. And I briefly sketched how it's used in a whole range of fields, from anthropology to sociology and pretty much everything in between. So far, so good. This is part one. What questions have you got? I'm looking at the chat on my second screen. People must be happy. No questions. Okay, that means we'd be ready to move on. Oops, sorry, one slide too many. That's going back. There we go. Okay, we got it. So we've seen a bit of why agent-based modeling and a bit of how it's used and some of the questions it can be used to answer. I want to now move on to talk a bit more about the how, not detailed how, but how also in contrast to other methodologies. Okay. So part two is about generative modeling. I called it this because that's really at the heart of agent-based modeling and simulation, this notion of generative modeling. And we'll come to that in just a minute. And here we have on the screen a picture of a big computer from the days when they had big computers filling rooms. I'll explain in a minute why I chose this picture. Okay, so modeling. What's the first thing to say? Models simplify reality. I mean, this is their purpose, right? Reality is complicated. We want to study it in a somehow simplified way. And that means, as there's a famous quote, that all models are wrong. By definition, by purpose, all models are wrong, but some are useful. And that's what we're trying to do today. We're trying to build useful models of real systems. Okay. So as I said, every model is a simplification of reality. The question is it a useful simplification of reality? Will it help us to answer the questions that, for example, we saw that some social scientists have or others? Okay, so the first, if you will, nugget here is model a problem, not a system. So when I talked about, as a real world system, what we want to model it, well, actually, no, what we really want is to answer the question. So the question might be, we have too much CO2 production. We want to move to biofuels, away from fossil fuels towards biofuels. So this is the problem, right? That being studied. It's this question of how to the energy transition, how to power the industrial network there. It's a secondary issue, the actual system which we have right now. So we model the problem, not a system. And that was going to help us to have a useful model of to help us answer the questions we have. Okay, this is our first nugget. Okay, what's our second nugget? Well, since all models are wrong, but some are useful, what do we mean by useful? Usefulness of a model is measured by the speed at which it is replaced. Now, this takes a moment to think about. What makes a model useful? Well, it's a more accurate model, or it helps us do this thing better. Well, no, the models have a purpose. That's to help answer some question. So actually, a really useful model helps us to move on with the question and ask the goal is not some model which will tell us some numbers and some projection. It's not the model itself or the output of the model. That's not the goal. not an agent-based social simulation, the goal is insight. We learn something from the model and then throw it away. And this is different to sometimes how we do models, as machine learning models, for example, right? Really, we don't care about the model, we care about the insight gained from it to help us address the problem at hand. That's our second nugget. Does that make some sense? Okay. Let's talk about modeling. So I mentioned in the introduction, the first section, that agent-based modeling is bottom-up. It's worth talking more about this. So we have to contrast it with something to understand it. So top-down modeling. Okay, so here we go. So this is a computer. It's a kind of analog computer. And the example here is, again, a kind of economic example. Again, so we have businesses and so on. And at the macroeconomic level, at the level of how does the economy work, there are theories, there are models, if you will. And they could say to a government, for example, the government of Great Britain, as advised, for example, about the COVID policy. Okay, let's talk economic policy. So maybe you should put up interest rates or put down interest rates, or we should adjust taxes or whatever. So there's different levers the government could pull, if you will, and that has an effect on the economy. And so this is an analog computer which physically, like with fluids, embeds those theories. And literally, they built a physical thing. So this is top-down modeling. If you do this, pull this lever, then the effect on the system will be that. What's the critique of this type of approach is that you don't account for the behavior of individuals. For example, individual businesses or better individual households. Okay? And this perhaps is some of the reason for moving to kind of behavioral economics things. This top-down modeling says you have a model of the whole system, you know how the physics of the system works. If I pull this lever, that happens, the money flows around the economy in this way. I know the physics of the system, and therefore I just, I can predict if I pull this lever, this is what's going to happen. It assumes you know the physics of the system, but that's often not the case with a complex system, and hence the critique. So as I said, the limitations, first, we have to understand the system in its entirety. And second, we have to know exactly how the components interact with each other. Now for a system like a complicated system, and we know if you push the accelerator, this is what happens. If you push the brake pedal, this is what happens. We are completely the system of the car. And I'd actually argue the economy is an example of a complex system. Traditional approach in many fields. Now, for agent-based modeling, it asks this top down. It asks, remember, how could the decentralized, heterogeneous, autonomous agents generate the approach here is not let's try and build the physics of the system. Is we're going to do simulation. It's a different philosophical approach to modeling. Okay. Here's another nice example of from nature of some regularity. This picture. Okay. So what's the generative principle? Well, we build understanding from the bottom up. And a famous quote from one of the pioneers of agent-based modeling said, if you didn't grow it, you did not explain it. And remember, again, social scientists are looking to know about causality and explanation. So by building something, by creating a model, we gain the idea. And there's an assumption, if you will, a principle. Complex things we observe in the system can be described. What terms? The interaction between simple units, agents we call them. That's right. The interaction between these networks. Often quite simple at determined finite rules end up with a complex behavior. So on the previous slide, when we had these birds, there's what each bird does is actually very simple. but these interactions between them, as I said, that's what gives the complexity. So this is the generative principle. Build understanding from the bottom up with the principle, the assumption that the complexity can come out of relatively some rules of interconnected networks of agents. Okay. So here it is in one slide. And this is the generative approach as manifest by agent-based modeling. So what to look at? Well, first look at here in the middle. First, we have an agent. So an agent is just a box. It has a state and it has some rules. And this is a typical computer science definition. I mean, as a reinforcement learning agent, the same kind of thing. We have a state and we have some rules of behavior. What those rules are, for the moment, is not important. What do we get? We get inputs from other agents. That's key. There's a whole set of these agents, the big one and the smaller ones, a bunch of them, and we input some other agents. Oh, the other agent just said that, or did that. We also get inputs from the environment. That's our second box here, the environment box. And so environment is like, oh, but it might be, I don't know, the temperature, or it might be the price of oil or something. So something that's not modeled as an agent. Okay. And then what? The agent is then embodied in the sense that it takes actions on itself. So how it, quote, feels, for example, changing its own state, actions to other agents, I'm going to give this to you, and actions on the environment. Okay, so the agent has inputs from the agents in the world around it, and it takes actions. Okay, so that's in the environment. And put together, then that's the outer box, which is the agent-based model. So an agent-based model consists of an environment and a set of agents who interact with each other. There's one more thing, which is crucial, which is this little line here. So the environment is embedded in the agent-based model, which notice is embedded in the real world, if you will, the whole screen, right? Where we have the modeler. So it's not like an agent-based model just comes out of nowhere. There's a modeler, someone or a set of people who create the agent-based model, the agents and the environment and their interactions. And it's important to bear this in mind, as we'll come and explore in a little bit. So there we have it, the whole, if you will, the whole of the generative approach on one slide. Okay, let's talk a bit more about the details. Okay, so what do we have in our agent-based model? Let's give some definitions. So we define an agent as a thing that does things to other things. And that's, in fact, just what I explained in the previous slide with the picture. So we have an agent state, we have agent behaviors, we have a model state and its behaviors. We need some rules. Well, what are the rules? I said they don't really matter, what they are for now. But what matters is that they are if you will, they're the agent's internal models. So the agent could build models inside itself, or for example, the environment or other agents. Behavior is what we can observe, the set of observable actions of the agents. And as I said, an environment is everything that's relevant. That's not an agent. There's other things. But if they're not relevant, we exclude them from a model because a model is a simplification of reality. And then we have discrete time. These are the things in an agent-based model. The agents, their states and behaviors, model state and behavior, there's rules for agents, there's behaviors, and there's environments. So you can think of an agent-based simulation as a kind of discrete event simulation, but a more thorough version of it, where the focus is not on the simulation clock, but on the agents and their behavior. Okay. Okay, good. So the rules. So we're in computer science, we're interested in how the rules work, right? Because we like algorithms. So the rules help us make decisions and transformations, take this person, and they give us actions and behaviors. The rules could be static, they could be dynamic. The rules, the multicolored thing, the inference engine you go and call. Genetic algorithm could be okay. And here in this little picture here, I have an example of a simple kind of rule-based flowchart style thing. Notice it's relatively simple because we're not trying to do a top-down model of the physics of the whole system, but just here, in this case, a top-down model of the relevant behavior of one agent. And there's interesting research, for example, on using reinforcement learning agents within an agent-based model. The two fit together quite nicely. So that's one way, for example, of doing the rules. Okay. So agents have state, they have rules. Boys, you might think it all sounds grand, very nice, but surely there's some limitations, right? And you're completely correct. So what are some of the limitations of this generative modeling, this bottom-up modeling approach? You have not been very responsive in the chat. I'm not going to ask you. But things that people can often identify are things like this.
Neil, sorry. I discovered that not every of them have access to the chat. So maybe if you don't, because now I received a mail saying that from one of them. So if you don't mind, I will give the access to the microphone so they can ask to you with their voices, maybe.
Yeah, that's great. Yeah. So okay. In this case, you'll be able to talk. Just pipe up.
Yeah, of course.
And then we'll go from there. Okay. Yeah. So limitations of bottom-up modeling. Yeah. Thanks for that. Helping out there. So no wonder you're all quiet on the chat because you couldn't access it. Yeah. I mean, you might say, well, it's great. We have these agents and their states and the rules and so on. Well, what about like how do we design these agents? You're making it rather too simple, where you said on this previous slide here, you had this nice little diagram, very nice. But like, yeah, where does it come from, right? So often we need to know data. Okay, not of the whole system, maybe, but at least about individuals. And then you might have been thinking, well, it's very nice. I had this little diagram of all the agents in the environment. Yeah, but that sounds much more complicated than doing top-down modeling, right? I don't just like build, one model of the whole system. I have to like do all these things with interaction. So the implementation is more complicated, and you're correct. And another limitation is it's just different. It's not traditional top-down equation-based models. We don't have a physics of the whole system. And in some fields, this is just different. It's just not what's traditionally done. I mean, what do you mean? You can't tell me how interest rates are affected by this monetary policy lever. Well, it's just a different way of doing things. It's a different mode of inquiry. So I would say that top-down modeling fails for complex systems. I'll say bottom-up modeling is excessive for simple and complicated systems. It's what we need for complex systems, but for the simpler cases, I mean, you can do it, but why not do some top-down modeling or something else? Okay. Does that make sense? Okay, good. So we talked about why agent-based modeling and the type of questions that get asked. And we also saw some examples, such as modeling epidemics. And now we've contrasted top-down and bottom-up modeling. And I've shown you kind of what agent-based modeling is at a conceptual level. And we've seen some advantages and disadvantages. But now a very important point, another, if you will, a slightly philosophical point, but very, very important when thinking about building an agent-based model. And the question is this: what are you trying to do with your model? That is, what's the purpose of this simulation you're going to build? Okay, I said earlier it's to answer some problem and so on, or some question a social scientist might have. Okay, but what's the purpose of your simulation? Now let's see if the voice thing works. Do we have ideas? What might be some purposes of building a simulation? If you can, try unmuting yourself. Let's see if it works.
I have a suggestion, and that is reduce costs.
Reduce costs. Good. Thank you for that. Yeah. What else? Other ideas?
Identify behaviors that might be detrimental to the collective and kind of control or design policies around it to prevent those behaviors.
Very good. That's quite topical these days with like people not being vaccinated or being vaccinated, for example. On any comment here, I'm just saying it's topical. Thank you. Yes. Good. What else? What other purposes might we have for a simulation?
To predict.
Prediction. Good. Great. Thank you. Others? Other people have ideas? Feel free to unmute yourself and say so. Okay, so we've got some good ideas. So the first one, I tried to frame very briefly. By the way, yourself, you're not for yourself. Yeah. So the first thing, we just want to understand more about the system. So we're not necessarily trying to optimize something or control something or even predict. We just want to understand. The next one might be explore. So more than just understand what's happening, explore kind of what if this other thing was to happen. So we might explore different ways of reducing cost, for example, as someone suggested. Then we had prediction. If I do this, then that might happen. Okay, yeah. It's worth saying that often people figure prediction as the first purpose of simulation, and it certainly is a purpose, but not necessarily the first one. Control. Someone mentioned control. How to control a system. And give some direction to it. Another one is how to design a system. So you remember our example right at the start where I had the picture of the building and people being evacuated. I asked the question I asked was, do we put the emergency exits? How many do we need and where should we put them? It's a design question, right? Which in that case was answered by simulation. Another question about purpose might be to validate. To validate a design or a decision or whatever it be. Okay. So a whole set of purposes of simulation. And the final one might be just to give perspective, just to look at things in a different way. So it might be complementary to another way of modeling things, for example. Okay. So a whole set of purposes. Some are more common than others, but it's very important to understand before I build a simulation, what is the purpose I'm trying to achieve? And in fact, there's a paper you can read, I think it's in JAS, where I think it's 21 purposes of simulation. These might be kind of the more common ones. It's very important because if you're, for example, just trying to understand a system, you're not trying to predict. And so when it comes to the question of, well, is your model valid? Well, how do you test that? You don't test it by trying to make predictions because the purpose is understanding. Right? So it all starts with the purpose of the simulation. Critical point. Okay, but also relevant is the different levels of abstraction. So this is from a paper from Tehran a few years ago, and they have a process here. The details aren't super important, and they're beautifully blocky here. But the key point what I want to make is, if we have natural language, so the language used by people like English or something, from this we can then choose a modeling paradigm. Do I use agent-based modeling here, or do I want to use equations, for example, equation-based modeling? From that, we then talk about modeling languages. And then from that, you then talk about the simulation programming language. So the key point is there's different levels of abstraction. There's levels of abstraction here in the model design process, but there's also going to be levels of abstraction within the model itself. So the point is to think about the purpose of the simulation, and then what levels of abstraction in going through the process. Let me give a case study to try and make these things a bit more real. And you can guess what, I chose one on epidemic modeling. But the paper I'm going to use here was published, slightly blocky thanks to the PDF, in 2016. So this is all pre-COVID. As I said earlier, epidemic modeling is a common use of agent-based modeling. Okay, and so here in particular, these authors, were looking at cholera. Looking at cholera in, let me see, I think in Ghana in Africa. Okay, so let's have a look at how they use this bottom-up generative principle. Let's look at the purpose of their simulation, and let's look at the abstraction that they did. Of course, you can always go and look at the paper later for yourself. Okay, okay. Figures from their picture. So this is, if you will, the high-level diagram of what's happening here. Okay, so they've got some rainfall, There's a threshold. If there's too much rain, basically the water gets infection, right? But there's also this interaction with where the waste is put. Do you put waste into the river, or do you put it somewhere else? Okay. And if you put it somewhere else and it runs into the water, then that's going to get really bad, right? Okay. So this is kind of known from the epidemiology literature, right? Why agent-based modeling? Well, it's people who collect water from the river, it's people who get infected, and it's people who dump waste. So there's decisions being made by people, and then of course there's going to be the interactions. Okay. So there's a modeling. Here's what it looks like. It's a geospatial model. So here's the actual thing. The blue is the water. You can see kind of the catchment of the water level here. And you can see shaded as different income levels. So some groups are more affluent, some are less affluent. So they did modeling, they looked at the catchment, and they had data, right? They had data about actual rainfall and so on and so forth. So they built their agent-based model, and the agents here are the individual people. There's interactions, and there's the environment, and so on and so forth. They had the rules, etc., etc. They did all the steps we talked about. And then here is a graph. You can say it's time on the x-axis, and then on the right axis is they're looking at how much of pollution goes into the river. Okay. The rainfall is the dots in green, so high and low rainfall makes a difference. And they can look at the blue line is the simulation, and then the red line is some other method. So what they're doing here is they're validating that their model does capture the behaviors that can be measured. Okay, so they did a modeling and they did validation. And having modeled and having validated their model, they can then use it to explore different things. So they're doing some exploration here. Okay. And so they could look under different amounts of rainfall, and they can look at what happens. And so the number of cases are these black bars, and the rainfall is this bar in blue. Okay. So what if there was more rainfall? What is less rainfall? What is there was a different way of handling I think it's cholera, right? Different way of handling the cholera. For example, should you isolate people? Should you not isolate people, etc. Right? So based on this, they can explore. And I think that their goal was to give some advice about different policy measures. Okay. Then they could draw some conclusions about the type of the epidemic in different scenarios. Very nice. Okay, so a nice case study. If you're interested in that one, please read the paper. Why do I show that? To illustrate what we talked about so far in the second part. Right. What's the take-home message? Generative models are wrong because all models are wrong, but they can be very useful. How are they useful? Because they can be replaced quickly. We gain some insight from them. What do we have in an agent-based generative model? We have agents, states, rules, actions, which lead to behaviors, the environment, and discrete time. And the key point when you're starting to think about building a model is, what is the purpose of this agent-based simulation I'm going to have? Good. I was going to ask if there's questions in the chat, but in fact, you can just ask the questions by voice. So far, we've had an introduction and motivation, and we've seen about this key principle of generative modeling. What questions do you have?
Hi, Neil.
Hi.
Would you discuss studying an epidemic model from the point of view of a computer simulation, just like this paper, versus studying it from the point of view of an SIR model, yes. So models based on differential equations, so far, which I believe are top-down, right?
Yeah, it's a great question. Thank you for that. That's a very, very a good question. So okay, I'll leave this slide up. So traditionally in epidemiology, they have these SIR models. And yes, these are top-down models. What they say that the population is split into, in this case, categories. The rate at which you move from one category to the other is determined by the maths comes down to a differential equation. There's a few key parameters. For example, maybe we're all familiar these days with the R, the reproduction number. This is one of the parameters in these models. Okay, so the great thing about these top-down equation-based models is there's very few parameters, they're relatively simple, and they let you do prediction. They say, if assuming we know that the let's say virus or whatever, like cholera, is this this likely to be infectious, I think they like to infect this many people, and it on average takes you, I don't know, 2 weeks to recover, or maybe not recover, whatever. Based on that, we can then plot when the peak's going to be and what we think the outbreak is going to be like. Great. That's the traditional approach. What's the difficulty of that approach is when you have it doesn't take into account individual people's behaviors. It assumes that everybody is in one of these three categories, and everybody in the category is the same. Right? The individuals don't matter. So if your level of abstraction is such that the individuals don't matter for the questions you want to answer, it's a great model. But what about, just to take an example from here in the Netherlands, what about when the government brought in rules about things you can and cannot do? What if the government says you have to wear a mask on public transport, or you can only go so many kilometers from your home? Okay, so some of these things they did and they didn't do in the Netherlands in terms of policy, right? Well, from the point of view of the SIR model, those things are predicted. We hope that they will change the infection rate and the reproduction number and so on, right? Okay, but that treats everybody the same, But what if not everybody wears a face mask? Okay, well maybe we can just adjust the parameters of the model a bit. But now hold on. But now people who let's just say, for the sake of argument, who aren't wearing a face mask are more likely to, let's say, get infected. But they live in a household with some other people who are then more likely to get infected. And so now what people do and don't do, and the interactions, which is the key point, start to make things complex. So we reach a state of a complex system. Okay, and then we might ask questions like, well, why don't people wear face masks? Now we're starting to get into social science. What are some of the motivations? What are the values behind it? And so on and so forth. Right? So the two types of modeling are seen as complementary, because the agent-based model, being bottom-up, is more intensive and more complicated. So in the literature, you'll find people do things like this. They say, for example, within a city, let's do an agent-based model, but for the travel between cities, let's do an equation-based model, right? Because the individual behaviors and interactions are not so important. So I think to answer your question, the two are complementary. And to go further, what we saw with the Imperial College model, which I showed you the GitHub page, they chose to do an agent-based model to get more precise, if you will, behaviors, more precise predictions, that's their purpose, than an equation-based model. And these are professional epidemiologists. They're very familiar with SIR models and so on, but they recognize that for their purpose, to better advise government policy, they needed an agent-based model. Okay. That was a long answer. It's a really good question. Did I answer it well?
Yeah, I believe so. It seems to me that when we talk about computational simulations, we're talking about the added complexity of individual choice.
Yes, that's right.
Perfect.
Yeah, and of course, in an agent-based model, you might model individuals as agents, or house agents. You can have multiple agents of different. I think later I have on a slide there's been a survey of why do agent-based modeling for coronavirus, and a survey of some of the works that have been done. And these surveys are by people who are professional agent-based modelers, as opposed to a lot of people who maybe don't have so much experience, who just kind of done something because it seemed the right tool at the right time. So it's interesting meta lessons learned about modeling epidemics. Okay. Good, thank you for that question. Are there more questions? Something of clarification or other questions about curiosity, either for the first or second part of this tutorial?
Hi, you mentioned the levels of abstraction.
Yeah.
So I was wondering if you want to explore some emergent behavior on a higher level, and you're modeling from the ground up. how do you consider like both of these things? Like, would you be able to capture behavior on a big scale if you don't look at it, or if you just look at the individual atoms?
Yep, good question. If I understood it well, there's maybe two points to explore and answer. So the first is the level of abstraction. You can choose what you want to be your agent. And as I said, there could be agents at different levels. So you might say, what's important to me is, let's say, the behavior of companies, like their hiring and firing behavior of employees. That was an example I gave in the first part, 100 million agents of the US economy. So in that, for that purpose, we don't care about the level of individual employees within the company. We don't care, right? We just care about what the company does. So we're modeling at a higher level of abstraction. The second point to explore in that question is this high level, the more global behaviors. Well, we get them anyway because they're the emergent system or semi-system level behaviors. So think of the fish again, right? We observe the system level of behavior of the fish doing their circles, even though here our level of abstraction is really low. I mean, we're just modeling like a simple fish, right?
Yeah.
That's one of the powers of generative modeling, is it lets us, in some sense, reproduce reality to see these global effects without knowing what the physics are behind the global effects. And in fact, in a complex system, you don't know the physics. That's the point. It's non-linear path dependency.
Yeah.
Did that answer the question?
So kind of, but can I ask
Can
I frame my question in a different way? So if you want to see what the emergent behaviors of particular characteristics at the lower level are, so do we have to define what the large level would be to actually define or identify those characteristics? Or
okay, so you're interested in the lower level behaviors.
Yeah, how lower level behaviors lead to emergent behaviors, and how to identify them or catch them.
Yes. So that's interesting. So if we knew how the lower level behaviors led to the emergent effects, then you wouldn't need an agent-based model, because you essentially know the physics of it. But that's the challenge, right? That's the challenge in a complex system, is you have this chaotic nonlinearity, and sometimes we can characterize it partially, but other times often we're a bit surprised. So going to the example of the economy, so they have this nice top-down model with all the flows and stuff. Well, that's fine most of the time, kind of. But then you had the financial crisis. Well, where'd that come from? Well, with hindsight, you could see it was brewing, but of course, as with hindsight, right? It came because we suddenly reached a tipping point of this. I think it was toxic debt of mortgages or something, right? So the point is that tipping point could have been later or could have been earlier. It's really hard to predict when it is, because you have this chaotic behavior in the system, right? So, yeah, this is the whole point. One of the whole points of agent-based modeling is, because of this generative nature, we get to understand these emergent effects, which are you can't write down the laws of physics or when they happen.
Yeah, thanks.
Good questions. I like it. Now I can hear and interact with you guys. I like your questions. Very good. One more question for somebody, otherwise we can move to the next part.
Yeah, maybe one last question about, I think you have also heard about the new trend of building model-based systems in the term of dreaming models, or something like dreamer models, which don't capture the whole environment, but are, for example, used to generate more data and to give also some explainability in the process what your agent, in this case a single agent, is currently learning and maybe also generalizing your behavior. What's your take on that? Or how does it connect to the research here?
Yeah, good. So I think that comes from the first of the three schools of thought about agents, which is a single intelligent, I think that's in quotes, agents. Yeah, so I think the connection would be that so an agent-based social simulation, we often have individual agents, agents modeling individuals. I mentioned they have states, of course, and rules, but how you architect an agent, okay, you can do it however you want. So the connection might be there, if you will. The agent has a model within itself, and that might be the connection of one way of framing that, or one way of introspecting within an agent. I think there's a caveat here, which is, it's particularly for the larger agent-based simulations, you don't want your individual agents, at whatever level of abstraction, you don't want them to be too complicated, because then the computation time of the whole thing explodes, right? Which is fine if you can run it on some HPC cluster, but you have to be aware of the the computational demands. Okay, so it's as generally keeping things simpler is at least the starting point, I would say. Interesting question, thank you. Okay, I'm going to propose we take a short break, just like 5 minutes or so. I think it's good to take a break and just stretch and refresh ourselves. But also you have an assignment in the break, since you're probably at a computer or something. If you haven't already got NetLogo on your computer, then can you go and download NetLogo, or see how much we can have a play with it? Do I have it? No, I don't have it in front of me. NetLogo is NetLogo, NetLogo. If you put it into your favorite search engine, it'll come up very easily. It's a Scala Java-based, JVM-based package, so you should be able to install it. And we'll try and use it a little bit, particularly in part 4. Try and do a little bit of hands-on, a bit of play with NetLogo. Okay, so let's have a 5-minute break. Stretch and refresh yourself and whatever. And if you can install NetLogo, that's great. We get to use that. Great. Okay, so I'll see you in 5 minutes from now. Good. Okay. So what have we done so far? We've at motivation, Socio-technical systems, and we've seen a few examples of how we can address a system. And in the last part, we then looked at the principle behind agent-based modeling, which is generative modeling, and we saw the advantages and disadvantages. And again, a second case study. Okay, let's carry on. Let's now get a bit more diving into things. So, social simulation tools. I'll talk for a little bit, and then we'll try a bit of hands-on. Okay, so 4 types. So of course, for building an agent-based model, you don't want to just use your bare hands. You could, right? So first of all, you could use a general agent-based platform. So for example, something like Jack or JX. So something designed for building intelligent agents or multi-agent systems or whatever. You could, don't know what that is. You could use that. Okay. The advantage is it's a powerful system. The disadvantage is that it's not dedicated for agent-based modeling, so the facilities may vary. Second, instead, you could use a dedicated AVM platform. So, for example, AnyLogic is a commercial system. Gamma, NetLogo, which I asked you to download just now. Okay, and these have the advantages of being tailored for it. Right. And here's an example, some very flashy 3D graphics and something done in AnyLogic. And this is some kind of factory situation where they're looking at shipping time and orders and so on. They do a simulation of the floor here, and they can give some dashboard outputs. Okay. There's another example. This one is a model called a repast. And then here they have some things moving around in the 3D space. And you can see here on the right-hand side how in repast they've got a drag and drop flowchart style. Okay, so try to make these things accessible. Third, besides these, you could use a library. So rather than using a dedicated platform like AnyLogic, or NetLogo, you could use a library. For example, a Python library. So like something like Mesa. There's a number of these one could use. And this is an example of Mesa. So here I have a Jupyter notebook on the right, and here on the left it's a simple square shelling model. So easy to use. You can see it'll do a little bit of coding, but it's straightforward in Python there, and that's easy to do here. They're doing a parameter sweep, so they're looking through the hyperparameters. It's just a few lines of Python. Very nice. And of course, you could use a general programming language. You pick your favorite language. And in fact, in the Imperial College epidemiology model, the coronavirus model, that's what they used. They used, it was C++ or something. Just, they just coded the thing in raw. Okay. So today we'll do a little bit of modeling with NetLogo. So here's the full URL. I'm sorry, I didn't have that view a bit earlier. Why NetLogo? Well, just to get a feel of things, a feel of one of the dedicated to ABM platforms, and just to play with things a little bit. Okay. So this is about screenshots from the NetLogo website, which is the URLs there. NetLogo is, you can guess, is derived from the Logo language. So it's a functional style of programming language, but meant to be easy to use. And NetLogo is used a lot in education to teach programming and so on. But it's also used a lot in Asia-based social science, social simulation and social sciences, because it has this low learning curve. So non-computer scientists, non-programmers can use it. It's, even if you don't know Python, you could use a program of some, but it's, it has a low threshold, as they say. Okay. So, and this is a tagline. Indeed, it's a low threshold, no ceiling. Probably until at least recently, it's the most commonly used agent-based social simulation platform. You can think of it as a programming language, but it's more of a scripting language plus a user interface with some drag and drop stuff. That's a bit of history. The key point to know that it's open source, written in Scala, it runs on the JVM, and there's even a web version where you can just run your models on the cloud. Okay, and the person who came up with it is someone a while ago, is pictured there. So NetLogo, I want to say, is not perfect. It's widely used, but it's not perfect. There's some limitations in the language, in part deliberate. It's not object-oriented, and you can think how object and agent somehow have a nice kind of synergy together. Scaling is okay, but it's language, or at least it's semi-interpreted. So there are some performance issues. Certainly, if you want to do 100 million agents, you might do better in C++. And well, as a disadvantage, it's not Python. Everything these days, you can actually look at NetLogo. And here's a typical screenshot. I'll show you some more screenshots in a minute. Okay. So the user interface, maybe you're already playing with it if you downloaded it, like I suggested, and you're trying some stuff out. And this is the interface tab itself. So often we have this visualization of the environment. It's called a world in NetLogo. So this is something to do with robbers and houses. And you can have the interface tab. So you can see the constant coloring, and to choose a victim, there's a if this and then that is fairly standard stuff. It's very standard if you're used to a bit of programming. Okay. And in the middle is it.
Hi, I'm sorry, Neil. Your connection is breaking very often.
Mm-hmm. Yeah. I just broke up. Sorry about that. So I was showing you the user interface tab. You saw that. Then the next tab is the code tab. And then the tab in the middle actually is the information tab, which is documentation about the model. Okay. So that's the NetLogo UI. Let's try it. So you've got NetLogo in front of you. File, menu, models library, and the models library is some available examples and other things. And let's see if we can do this. That should load the ants model. And then once it loads, you'll see it on the user interface in front of you. and there's a button mark set up, and then go. And if you do that, you should see some ants moving around. And hopefully there's ants moving around on your screen now. I'll give you a minute or two to try it.
Hi Neil, I'm sorry, your connection broke again while giving the tutorial. Yeah,
so I'm suggesting we try out NetLogo. Yeah. So the model ants. So it's File menu, Models Library. You'll see lots of model ants is the one you want. And I'm hoping by now you'll see some ants moving around on the screen. Yeah, there's nothing I can do about the connection. So there's simply nothing to be done. There's lots of models in the model library. Lots of, you can play with them later if you'd like to do that. And if you want to, you can look at the code tab and have a look at how the ants model is implemented. And of course, ants are not exactly a complex social system, but notice the emergent effects. If you think about it, ants' behavior is actually quite simple. And indeed, the rules encoded in this model here are simple, localized rules. But we do get emergent behavior. We do get these pheromone paths, between the whole base of the ants and the food. And if you think about it, there's actually so-called swarm algorithms where people, ant colony algorithm, right, where people solve optimization problems. Right. So here we're just doing a simulation, but the same principle is and again, complex behavior emerging. So complex behavior emerging out of simple localized interactions. Is it good? Are your ants working? Okay, well, I'll do a bit more talking. So, how do these things go together? So the interface tab and the code tab, by the way, your screen might look slightly different. There's this setup button I mentioned. That's the setup one that starts things out, and then the go actually does things. But when the setup button, well, how does it work? In the code, there's a procedure which says what to do when the user clicks on set. And normally what you do in setup is you initialize the environment. Remember, agents and environment. Okay. Okay, let's say a little bit more about I suppose. Is it working for you? And NetLogo doing something?
Yes.
Yes, it was.
Is it working for you? NetLogo? Did you get NetLogo doing something for you?
Yeah, I got to see the ants moving and checked the code.
Good. It's working at least. Okay, good. Let's talk a little bit more about it. So in NetLogo we have agent that corresponds to agents, to the environment, and you remember I had the modeler as the outer box. So that's actually explicitly done in NetLogo with what's called the observer, which somehow is the kind of controlling agent, which then has the modeler behind it. Okay, but NetLogo does have some terminology. NetLogo has some particular terminology. So agents are called turtles. That's his historical regions, and locations, if you will. Then here's a fragment of NetLogo code. You do this kind of stuff. Ask a person, Fred. Okay. That's thread, ask the neighbors to do such and such. Okay. Typical style coding, as you say, it's a bit different to Python. It has a certain peculiar style, but once you get used to it, once you get used to this kind of particular coding style, it's, you know, even social scientists, people who are not used to programming, can get used to it and implement models. Okay, good. Let's try something else. Let's try something a bit more interesting than ants. So let's try the model called Rebellion. So it's file, models library, this time social science, not biology. And then the Rebellion model. So Rebellion, whether people follow, and there's different people. And the interesting thing is, just like ants, they interact with the neighbors around them. You're rebelling, and then you're like people around you. Okay, it's based on about 2002. So try that. File, models library, social science, Rebellion, set up, and then go. Hit it. Click go and have a look. And you start parameters you see on the interface. I'll give us a minute to put things out. And again, in it's a very simple agents. It's really simple agents and behaviors, interactions, give some complex. Right. So for example, does the rebellion succeed? More than 50% or whatever it is I'm taking. How sensitive is it to the initial parameters? So questions of causality and explanation, things in social sciences. As I mentioned, try the parameters. Try watching an agent. You right click on it and you click watch, and you can look at, drill down on one agent. And if you want to, you can try the visualization 2D or even the 3D. Now, we're not going to do this writing here, but later you can try write a reporter, a NetLogo reporter, which says true when there's a rebellion. And I look at how that, and programmatically look at how that varies over time. We're not going to do that now. Don't worry, but you're welcome to play with that later. The model library not only has lots of models, the model implemented. So if you go to that middle, they explain the history and the purpose of the model, and sometimes they tell you with different things you can try. And they have little exercises in the ones designed for education. Is it good? Maybe in front of you, the screen is full of rebellion of lots of red agents, or maybe not. But the interesting thing is then when you get these kind of waves of like, what do you say, a revolution and non-revolution happening over time. Okay. So NetLogo can do a lot more than just these two small samples. It's GIS, so geographical data. You can link it with system dynamics models. You can do distributed things. There's some experiments. You can actually interface it with Python and also R for statistics. Scalar things with NetLogo. Yeah. And of course, NetLogo is one of the tools based simulation. There's others available. So I want to start towards wrapping up this tutorial. In this part, I briefly discussed a dedicated agent-based platform versus using a library or even just using raw code. We play with NetLogo with its ideas of patches and observer for agents and environments, and what we'll do in a minute is we'll explore a little bit more on that civil society rebellion model. Other questions after you've played with NetLogo here? If you have lots of questions about NetLogo itself, I'm happy to take them. Happy to take questions about NetLogo, though of course we could always do that later offline.
Well, one small question, is there also a way to define the environment size, so to upscale the whole simulation?
Yes, you can change the environment size. So the default, when you just do file new, there's a you click on properties, I think, in the menu and in the toolbar, you can change the size of what they call the world. So yeah. For example, we use NetLogo in a work where we're modeling a city, and we use GIS for data. Much bigger world there, and then it's not just also grid.
Is there a model in the model library with GIS data?
Yes, that's right. Yes, I'm sure there is. I don't know off the top of my head. I'm sure there is one.
Oh, okay.
Yeah, I don't know, you can have a click round and play. To import a model. The standard format GIS data. Yeah, we did that for a paper, and we did that. We had the data from OpenStreetMap. We just imported OpenStreetMap data straight in. Worked fine. A little bit slow because of the size, but no problems. Good. Let's move on. I wanted to just reflect a bit on the modeling process. I mentioned this earlier in the sense of it's not just the model you build and even its purpose, it's also the modeler itself. And this is worth reflecting on. Now we've just had a little bit of a play with one model. Right? And on the screen, the picture I chose here is some kind of, you've probably been in these, right? Probably in these things where they have whiteboards and sticky notes and stuff. And like, well, actually, this is some of the practices of agent-based modeling and what's called participatory design. Out it and then things up. So how do you build an agent-based model? Well, I talked earlier about you have different levels of process of choosing the methodology and then the language and so on, and the purpose. Well, I mean, end to end, it looks something like this. We do start with the purpose of the simulation. Why am I building the simulation? What problem, what question am I trying to answer? Then, okay, we need to think about our actors. These can become the agents, of course. But okay, if I'm looking at the coal-powered plants and the biomass plants from our first example, well, who is it important? Who are the important actors? Do I need to model the government or not? Do I need to model the fishermen or not on the river? I don't know. So who are the relevant and important entities/actors? Then data. That might mean data like time series data. It might mean data where you go and interview somebody, right? You go interview the fisherman, right? Then a high-level design, followed by more detailed design, so a two-step process. Top-down design. Then you have to implement it, calibrate it, etc. And then you have to verify and validation. And I'll come and explain a bit more about that in a minute. That's very important too. Yeah, this is the suggested methodology, and in the references on my last slide, I have a book which explains these steps in some more detail. It starts with the purpose, we then go through and ends up with verification and validation. Okay. I think I talked about this earlier, about the abstraction. Okay, so there's some modeling standards. The most useful one is what DD. It's now in version 2 or like 2+. It stands for overview, design concepts, design details. It's a bit like the top down, like I just mentioned, the high level and then the more detailed design. It's a way of not so much a design process, it's more a way of documenting an agent-based model. And that's been a trend in the literature more recently. People said, like, here's my model, it does that. There's my model, it does that. But how do we reproduce your model? Can you clearly describe it apart from the code? And ODD came out of that. There's some other initiatives. OpenABM is nice because it tries to encourage model reproducibility. Okay, so it based on a repository for models. I've mentioned data, and someone asked earlier a question which was related to this. There's two schools of thought. One is simple. You be as abstract as you possibly can. Keep it as simple as possible, almost like you're going a little bit kind of top down in the design. The other is the opposite. It's descriptive or data. You start with as complex, as realistic as you possible, and you only simplify when it's turned out to be justified to do that. And there's been a debate: should you start simple and grow it, or should you start realistic and abstract it as needed? There's no one answer, but it's good to be aware of these two approaches. Here it is in pictorially. So on the left-hand side here, the KISS starts with as simple as possible, and you grow it to be complex in whichever aspects are important. Whereas descriptive says, well, try and be as descriptive and accurate as you can, and then you simplify it or maybe change it as necessary. Right. And Edmonds and Moss is a good introduction to the two approaches here. Again, neither's right, neither's wrong. It depends on what your purpose is and what you prefer, and also the design process itself. It's good to be aware of the. To touch on verification and validation. This is very important. Terminology. I won't ask you what it means, but I'll ask you how you might do it. So verification first. Verification is what I implemented matches what I wanted to do. My code does the right thing according to my design. And by design here, I mean the conceptual model. That contrasts with validation. Validation is what I wanted to build matches the reality adequately. So verification is I built the right thing. Validation is the thing I built does the right thing. So they're related, but you see the difference. So of course you have to do verification first, like did I build the right thing? Sorry, verification, did I build it right? Before you do validation, did I build the right thing? So both are important. So my question is, okay, fine. We build a model, we had a purpose, we built a model. We now did verification and validation. Well, how do we ensure, how do we do verification of an agent-based model? How do you do validation of an agent-based model? How do we ensure these properties? Are there thoughts you have? How might you do these things?
We might try to reproduce some results that are known that the model I'm creating is supposed to reproduce.
Very good. Good. Reproduction or historical replay. Very good. Yes. What else could we do?
Test extreme cases.
Good. Very good. So that's more on the verification, whereas the kind of the historical replay is more on the validation. Good. Yeah. Good ideas. Other people? How could we ensure these properties? How do we do verification? How do we do validation? It's a bit not easy, right? When we can think of some things, and those are all good ideas, but it's a bit not easy. And it's one of the more difficult things, I think, in agent-based modeling. Defining the purpose is not difficult, but important. Building it is, okay, maybe it's a bit of work needed, but actually the more difficult part is the conceptual model, and then its verification and validation. Okay. So for verification, here are some ideas. I think someone suggested checking extreme cases. So checking different parameter settings. So some of the things we can do: have an expert check the model, if they can read the model, check the output. We can do just like in software engineering, we can verify components. You can even do formal model checking. Maybe we can look at different input parameters. Is it seen to be doing something reasonable? We can try interactive tracing. So I said you could like watch an agent, just watch an agent all the way around and see what it does. And a powerful way of doing verification is the last one, which is to implement it more than once. Either with different people implement it or implement it in different platforms or toolkits and compare. So verification is actually maybe that's a little bit bit easier than validation. So my definition of validation, you remember, was my model adequately matches reality. Yeah, but what does that mean? What adequate mean? What does that mean? So I mean, some thoughts on that. Does it replicate in a valid way? So that was just mentioned. Does it predict? Does it have validity for predictive purpose? And does it have validity in a structural kind of way? So in other words, in validation, is it fit for purpose? It's how I think about it. Does it match reality in a way that's fit for the purpose of the model? So again, it comes back to the model's purpose. Right? If you're not trying to reproduce history, then testing it on reproducing history is the wrong test to do, right? It just doesn't answer the question of validity. Okay. Right. Just some things we can usefully do. Having a model which, when we look at it, has validity. Right. Validate the assumptions, and again, for both of these, you might bring in experts to do it. Right. And then this last one. Look at the transformation. Look at compare with the real. So transformations. You know, it started on this time when the weather was like this to the ones for the real system, and maybe you can do a test. But again, what we do for validation depends on the purpose of the model. Okay. So I mentioned experts, validity, assumptions. We can do in a structural way, the structure of the model and the data, what we assume there. And when I talk to the system, well, not just comparing the graphs, you do statistical tests. The validation. Linked to validation is, and very useful, is doing a sensitivity analysis. So here the question is, of the observed. So here in sensitivity analysis, the question is, of the observed behavior, which of the input parameters gave the most effect? So, you know, the variability we see in the output, how sensitive is that to which of the input parameters, right? And actually, are the precise values important or actually not so important? Sensitivity analysis is very useful sometimes for answering some of the questions that's, okay. Okay, there's a bunch of stuff you could do. Okay, I don't think I want to talk about that. But I do want to show you the kind of output of sensitivity analysis. You get these nice graphs here, these nice pie charts. So we had some different input parameters. So we have the yellow, the green, and the pink different input parameters. Some will have distributions, and we can see, look, as the output, look, the pink one, right, for output A, and it's also the most important for output B, but a bit less important, right? So again, it's looking at which the inputs are responsible for the variety seen in the observed outputs. And there's toolkits which can help you do this in a semi-automated way. So verifying validation according to the purpose, and sensitivity analysis, looking at where's the important variation. I don't think I'll the example of that. But it is worth showing. And so here's some matrix plots. I'm looking at the heat maps of how certain outputs vary depending on inputs. And here's a geographical based one where we've colored here the different, I think it's houses according to the effect. So sometimes visualizations can be useful in both doing verification and validation as well as sensitivity. Okay, I think I'm not going to ask us to go back to rebellion. You can try this later. So the rebellion model, what you can do is you can ask some sensitivity questions. For example, how sensitive to this parameter? Okay. We'll not do that now. Okay, a few concluding remarks. Let me see about model use. Good and bad models. Okay, what makes a good model versus what makes a bad model? Okay, so I mentioned sometimes before we can have multiple models. So we can re-implement a model. What makes a good or bad model? Well, here are some guidelines. Clarity in what you're trying to do, clarity in the model itself, clearly either doing simplicity or descriptiveness, and a good model has lots of assumptions which are made explicit. It's okay to have lots of assumptions because remember, models simplify reality and all models are wrong, but at least let's be explicit about in which ways we're wrong. Bad models do this kind of stuff. Well, we just chose this value for the parameters because it kind of made it work and it kind of matched reality, right? Let's just throw lots of stuff in because we can, right? Yeah, I mean, it's basically the randomness and there's not, there's nothing else there, right? Or no verification, no validation. If you read papers in the literature, you can fairly quickly see this is a good model or bad model in terms of the modeling side here. You can often see that quite easily based on these kind of criteria. Good models, bad models, and there's good and bad uses of models. So in good, you read a paper, it's clear why they did these experiments. And the outcomes of the model when they're connected back to the system under study. And there's explicit statements again about limitations or interpretation. On the other hand, you read a paper and, well, they ran the model once and QED, not so good. There's no statistics. Look, it went up really, yeah, okay. There's things like, hey, we did this really cool AI agent-based modeling stuff. Yeah, and right, so these kind of things, good and bad models and good and bad uses, abuses, if you will, of agent-based modeling. Okay, I want to conclude both this part and then the whole tutorial. So we're talking here about the process of building and key verifying and validating a model. And indeed, it's garbage in, garbage out, isn't it? Right. So the methodology is important, the assumptions are important, and the verification and validation. Our experience is if you don't do it, people will just reject your model. You built this thing, so what? Why should I rely on it? What's the evidence for it? You do this thing, someone else does other things, so what? Right. So stakeholders are not involved in the process. Examine the model, they'll just reject it. It's just another black box. I want to conclude briefly with a few resources and leave some time for some questions. Resources. Okay, so let me just summarize. Generative science, this generative principle, is a successful way of modeling which complements top-down modeling. What are some of the things moving forward? So there's best practices emerging, as I mentioned, this ODD, for example, description. Second, a current trend is agent-based modeling and either data mining or using learning within the agents, particularly reinforcement learning. Another current trend is multi-model, so connecting multiple models to do. And this has been facilitated in part by a new generation of computational tools, mainly using Python. These are some of the current trends. Here's a list of platforms. I mentioned some of these before. These are the URLs, so you can check them out if you'd like to. And here's a reading list. There's lots of reading here. If I was to read one, I would recommend the first book. There's a picture. It's a Springer book. I recommend it not just I recommend this book, not just it was written by people from TU Delft. I wasn't involved in writing the book. No, I recommend it because it's a thoughtful and thorough perspective, both of the philosophy and of the methodology, and then some case studies. So it's a good read, I think. There's a number of other good books and articles here which I've cited.
Can you show me the URLs again, please?
This one, yes. take your screenshot now to get your URLs. Yeah. Also, if you put most of these in and put like agent and the word there into your search engine, you'll get the things there.
Okay. Yeah. Thanks.
You're welcome. And the books, I can put this slide back up later. Well, I'm sure I'll be able to share these slides, or at least the recommended reading list. I also wanted to mention this. So TU Delft has some what's called open courseware. So these are courses you can take, they're short courses. This is a course which we produced on agent-based modeling of complex systems. So you can go and take this course if you would like. This is done by my colleague Igor Nikolic. It's very good. It's a really good course. And there's and TU Delft makes no money out of this. It's funded by the Dutch taxpayer, free for all, but a nice introduction to agent-based modeling and suitable for someone who has no computer science background. Right, with a little bit more time, if you have some questions, be very happy to take them. Feel free to be in contact with me. Feel free to email me, be in touch. I'm happy to do my best. Thanks here to a number of people who helped make this presentation. How can I help you with any questions you might have? Who has a question?
Hi, thank you. Thank you for the wonderful presentation. My question is regarding a slide that you showed for the verification. You mentioned some formal methods of model verification. I was just...
Oh, yes. I'll go back to the slide. There's no point. I just mentioned. I just put the word up. Yes. Yeah. So this is so the question, of course, is this is verification. This is, have I built the thing I built is the thing that I wanted to build. Verification in a software engineering sense. Right? So formal verification is where you take your code, so let's say NetLogo, and you run it through, say, a model checker, and you're running it against some property. So you need to check a property. Right? So the property might be, for example, I don't know, no agent.
I'm sorry, you broke. The audio broke. And,
yeah, so,
and we're still seeing the colophon slide instead of the slide.
That's right. I don't have a slide about formal verification. So I could go, but I only have. That's right. So you need some property model check. Is your code, your implemented model, and some property, right? And you put it into a model checker, and you. So the same does for example, kind of Python same idea. Did that answer the question?
The audio broke in between, so but I'm guessing that we use some formal model checker and define some properties of which we are interested, and use both of these to check if the model is valid.
Yes.
Yeah.
Exactly. That's right. Yeah.
Thanks. Thank you.
So in some sense, there's nothing special about an agent-based. Yeah, it's in that sense.
Yeah. Thank you. Thank you very much.
Thank you for the question. Questions?
Hi. Could you re-describe the differences of the approaches KISS or KIDS, because I wasn't completely sure what that meant.
Yes. Yeah. Oh, I will do that. I will go back to the slide for that. I can put it up. Yeah. So here the debate is how to approach modeling for an agent-based model. Just paging back to one of our slides. That's the sensitivity analysis. Paging back to slides. Okay, here we go. Good. So hopefully I've reached the right slide. Good. Do you try to be as simple as possible, only become more complicated, more complex, or do you start with as realistic, if you will, complex as possible, and only simplify that when the simplification is justified? So here it is pictorially. Here it is on the left-hand side, and there's pictures from the Edmonds and Moss paper. So essentially, in KISS, you start somewhere down the bottom, and you develop it incrementally. You grow the complexity as needed, but only if needed. Right? Whereas kids starts, you try and be as realistic as possible. You throw it all in, right? That everything that you throw in, and you only make a simplification, an assumption, if it's warranted to make that assumption, right? If, for example, if it's sure it doesn't affect the system behavior to, I don't know, ignore the day of the week, then you ignore the day of the week. That's the gist of it.
All right, thanks.
Did that help?
Yeah. I wasn't sure where exactly would one use the descriptive approach. Yeah, you mentioned it right now.
Good. Oh, happy. More questions?
Yeah, another question. What exactly did you mean by low heterogeneity that makes a bad model?
I only caught half of that. What exactly did I mean by something? I missed the last keyword, I'm sorry.
The low heterogeneity in bad models.
I'm sorry, I still didn't catch it. What is that?
Low heterogeneity, where you described what makes a good or a bad model.
Yes.
There are some characteristics of bad models, and there's a low heterogeneity.
Yes, I'll bring that slide up again.
Yeah, what exactly does that mean?
Yes, good question. Yeah, yes. So there's good models and good and bad uses of models. Let's page the slides again. Okay, good. Right, low heterogeneity. Right. So remember, in a top-down model like the SIR academic models, everyone's the same. You're just in categories, right? So and they have limited freedom to act. There's very few choices. Then okay, it's an agent-based model. Is it a helpful model, right? So it might be that assumption might be justified in that design. It might be fine, but without an explanation, it's, well, why is there so limited freedom for the agents, right? Why there's so few choices? I'm not saying it's wrong. It's just an indication of maybe the design process has been not thought out, right? Likewise, the next bullet, where here the freedom to act might be a lot of freedom, but if it's mostly stochastic, it's just random, that means the agents are acting randomly. So it might be appropriate, right? But you need to explain why it's basically the decisions are random, right? Does that make sense?
All right. Yeah, it makes sense. Thanks.
Yeah. It's a good question. You asked some very good questions today. Thank you for them, and thank you for everyone who's done some interaction, despite our platform limitations, and for the questions. I appreciated that.
Well, thank you for the presentation.
So I suggest we wrap it up here, because at least in my time zone, it's nearly 6 p.m. on a Friday. So thank you for staying to the end of the summer school. I'll put up again, which has an address. Feel free, happy to answer questions or just discuss with you, also within TAILOR potential collaborations. Thanks again for your attention. I hope you've enjoyed it and felt you've learned something. Wish you everyone a pleasant weekend.